My name is Tiarra Smith, and I present a mathematical model of heart rate baroreceptor control and sympathetic and vagal activity. So we will cover heart rate variability, studies of heart rate variability, common methodologies used, and we will conduct three analyses, and then we will present our results from those analyses. So, according to the CDC, the Center for Disease Control and Prevention, the leading cause of death in the United States is heart disease. Specifically, using data from 2022, over 700,000 Americans died from heart disease. And it was also found in a study in 2013 that the leading cause of death in the United States from the past 20 years has consistently been heart disease. Now, heart rate variability is a non-invasive tool for autonomic nervous systems, sympathetic and vagal activities. And HRV, heart rate variability, it can help provide predictions for cardiac events over various amounts of time. So, HRV studies throughout the year, starting in the year 2000, a study was conducted to separate HRV into high and low frequencies. They used bifurcation theory of a nonlinear system to study the high and low frequencies. Then in 2001, a demonstration of the characteristics of the beat-to-beat fluctuations in the heart rate for sympathetic and vagal control. But these studies primarily use animal metrics and parameters. Skipping to 20 years later, a study using similarly nonlinear HRV analysis to uncover the hidden signals and to enable a faster prediction of the cardiac events. Like I said, HRV is used to help predict these events, so we want to try to increase or decrease the time it takes us to predict them. The study mainly focused on the electrocardiographic signals as an initiative, the ECG. And then in 2025, studies are being conducted on how organs affect HRV. Our study primarily focuses on the physiological conditions that affect the HRV signals in your heart. So, the main methodology to study HRV from previous studies were nonlinear. We use the time domain and frequency domain analysis. They're also the most common use. Time domain analysis uses a statistical index to describe the magnitude of the variability. Frequency domain is used to highlight the relations between autonomic nervous system activity. So the sympathetic and vagal activity, what is the relationship between those? These frequency powers reflect the changes in the sympathetic and vagal activity. These equations at the bottom are given. These are our firing rate equations that we used in our analysis. I will further explain that later in our presentation. So starting with our positivity analysis, biologically speaking, your heart rate cannot be negative. So when we did our study, we had to have a positive solution. So that means we had to have a non-negative initial condition and maintain non-negative. If the initial conditions are non-negative, the system will not produce negative concentrations. Therefore, if A1 equals 0, the terms A0 and A2 will prevent A1 from becoming negative in the system. And A1 is represented for the sympathetic activity. In our vagal activity, when n equals 0, nm has to be greater than 0 to ensure that nt increases. The non-positive term in our equation, the kf term, though it is non-positive, it does not make nt negative. Each equation includes these terms that structure the system to remain non-negative and preserve the system's positivity. So what are the A1s and what do they stand for? Using the Warner model that was presented in the 2001 study, the variables presented the dynamic behavior between A1, A2, and A3, which influence the external inputs and internal system parameters. So A1 is represented by norepinephrine, which is a neurotransmitter. The norepinephrine concentration at the nerve's ending, A naught is the norepinephrine's concentration in the blood, which can also be used as plasma, another term, a common term. And in the equation, it reflects the sympathetic nerve firing balances between nerve conditions, K, NF, ST, and then A2 is the norepinephrine concentration at the active site. A2 is found to be influenced by the norepinephrine concentration's distinct target points, which is the terminal point of A1, and it's clear for A3. So leading into A3, A3 is the concentration of the compounds. BT just are some to cover some of these other terms. The BT is the substance. The K's represent the rate of reactions constant, and the N is the fibers. To conduct our equilibrium analysis, we started at some point T to bound it, so we could get our equilibrium point. And during our study, we found that A1 and A2 equaled each other. We wanted to get a steady state specifically for A3. So for the vagal activity, vagal activity is associated with the acetylcholine neurotransmitter. The vagal equations consist of the average number of vessels in each acetylcholine charge nerve, which is represented by NT, and then the maximum number, which is represented by N. In our equilibrium analysis, we assume that NT and NM are at the same steady state, so we were able to solve for N, and then N was also in our C2 equation, so we were able to solve for N and then put it into the C2 equation to get our C2 equilibrium point. The acetylcholine concentration in the vessels are C1, so that's what's inside of it, and then what's outside of the concentration is represented by C2. So for our stability, given the equilibrium point relies on the norepinephrine release, diffusions, receptor binding, and clearance rates, the changes in the parameters could cause the stability to shift. This leads to oscillations, delayed recoveries, or autonomic dysfunctions. For stability, we found that K5 plus K3 plus K4V over V2 greater than 0 is always true, since the given parameters are positive. This was derived using a Jacobian matrix as well, using those partial derivatives. The real parts are negative due to the decaying oscillations. At least one positive root can cause the system to be unstable. Same thing for our vagal analysis. Given lambda 1 and 2 at the bottom, they're responding to the stable system for the analysis to be stable. With a stable system, this provides evidence that the activity decays over time, and also that the physiological parameters must remain positive. So once we got our analysis finished, we conducted a simulation of 60 seconds. So using real time rather than other data, we did a 60-second time frame and we did our model's parameters. However, biologically speaking, we had to bind our model because if we did not have a minimum heart rate, it could produce a negative heart rate within the simulation. And we don't want a negative heart rate. So we bounded it at 30 beats per minute as a minimum and 70 beats as our initial state. It has to be 30 because it was found the vagal activity is a strong receptor to the heart. It decreases your heart very fast. So if we bind it, it stays at 30. So the autonomic oscillations and parameters reflect the firing rates, the initial conditions of the neurotransmitters are given at 0.5, and then we bounded it for our time simulation. So our time domain analysis specifically starts at 50 beats in our first subplot and rises to 70 beats to exhibit the oscillations reflecting the periodic fluctuations in the heart rate. This is a clear indication that ANS is present. We're studying the sympathetic and vagal activity, which is ANS. The norepinephrine concentrations are in our second subplot, and there's a 60-second time frame. In blue, norepinephrine starts high but drops as the amplitude lowers. ACH starts low and then it begins to rise slowly. He starts low. and then begins to rise slowly to maintain a smoother oscillatory trend. But as we see in it, it's moving a little bit faster. It has a little bit more fluctuations than our norepinephrine. And then our power spectrum is an indication as to where the highest frequency was at. And it's indicating at 0.25 hertz. And then there's a tiny indication at 0.25 hertz is the big spike. And then 0.5 hertz is the little tiny one. So to kind of zero in on that specific frequency, because it's showing such a dominant frequency, we did a frequency domain analysis. The firing rates are presented again. Each firing rate represents the oscillatory neural drive to the heart, and each has a physiological significance. Any levels decay initially and is more stable in this subplot. And each of the frequencies are, as you can see, are sinusoidal. And our vagal activity within our vagal activity is moving a little bit faster, has a higher frequency, so it's oscillating very fast. Given that our parameters are bounded from 70 to 30 beats per minute, this is kind of like a resting state, so we see a more active vagal activity. At high frequencies, the neurochemical responses moves out and interprets the neural activity over time. In our neurotransmitter levels, the neurotransmitters are moving rapidly because it's a resting state. So we see a little bit more of a response between the acetylcholine. Now, the third subplot is just a zoom in on our previous subplot one. It's not much of a variable within the frequency domain analysis compared to the time domain. So our results, the time domain simulation presented the autonomic system's ability to naturally stabilize the heart around the equilibrium. The physiological realism is supported by the system remaining positive, stable, and bounded. Due to the location of the peaks, the model structure is kind of validated, and combining the time and frequency domains analysis created an accurate study of the autonomic control of the heart, specifically within humans and adults. Overall, we did see a prominent vagal activity within the presence of this model. So that leads to our future work. We want to maybe use a little bit more real data. We did real time, but using real data from ECG data based on the further examine parameters, based to further examine the various parameters. We bounded it from 30 to 70. But if you were to look at exercise parameters, what your heart rate looks like when you're exercising, stress parameters, which activity is more prominent, sympathetic or vagal. And we could also do it clinically. Medical drugs, how does that affect your heart rate variability as well? These are my references. And thank you to my mentor and to my professor. Thank you.